for also featuring this very exciting topic of isogeny-based cryptography at this school. How many people in the audience have heard of isogenies before? Maybe you can switch your hands. Oh, okay. How many people know what it is exactly, like the definition and everything? That's fewer people, so I'm very happy to point out that I will explain these things, so that you're in the right place. Oh, sorry. I can hear myself very loudly, but apparently. Yeah. Okay, isogeny-based cryptography. It's a part of post-quantum cryptography. There are some constructions. I will talk about all of these things, but before I get into the technical details, I want to first explain a little bit about the big picture of what isogenies can do for us in cryptography. And one of the things it does is it produces exponentially sized graphs, where exponential means, like in the number of bits you need to write down data about these nodes and edges. And of course, when graphs turn out to be exponentially big, which is nice for cryptography, so there's a big asymmetry in how much work you need to do to write down the thing, and how much how many different things you can get. We can walk around on these graphs, so there are algorithms to like take the neighbor and find locally, walk around on these graphs, but of course you can't enumerate the whole thing because it's so big. And what's also nice is that these graphs have typically, I mean, there's some variants of this, but the cases we like for cryptography have fast mixing properties, so you can also get to any node very quickly using just a short path. But just given two nodes in the graph that you can find by taking a walk, for example, it should be hard to find a path between these things, right? So that's also why we need many nodes in the graph. And this, apparently, for some choices of these graphs, also happens for quantum algorithms, which is nice for post-quantum cryptography. Yet, despite all of these things, right, so there should be kind of big random graphs, and it should be easy to walk around, but hard to recover paths, there should still be some kind of nice structure that is mathematically described. And that's what allows us to actually make sense of the structure of this graph and use it for public key cryptography. Right? So it's just random, it can't really do anything useful for us. But these graphs are random to a large extent, but there's still some structure that allows us to do stuff. And I will have examples of that later. Okay, and this is these are things that isogenies can do for us, and it seems like there's not many alternatives if you want all of these properties. I can't think of any, in fact, so isogenies are the only way of getting all of these properties for big graphs all at once. Okay, how do we do crypto on graphs? This is also an unfamiliar concept. Most of the time people think over finite field and with lattices and so on. So how do we use graphs? And this part is here to convince you that we're already doing that, just not in the same notation. But one example of this is just a normal Diffie-Hellman key exchange, right? So it's defined traditionally over a finite field. Nowadays you just use a different kind of group. And you have a generating element called G, and then Alice and Bob take secret powers of this generator element, or scalar multiples, and they exchange the powers, and then they apply their own secret again, and they get the same thing. And the reason this works is because this exponentiation is commutative, so they get the same secret. I guess everybody should have seen this before, very standard stuff. But my point now will be that this is actually an example of this graph thing. So the starting point for that is that there's actually a detail in this Diffie-Hellman key exchange that's very important, but it's often kind of skipped or mentioned as an optimization, but it's really crucial. And that is that if Bob just computes this power naively, he just computes G times G times G many times, it actually takes the same time as what an attacker would invest to recover the secret. Right? You just force search for the public key, and then you found it, and this is essentially the same effort. So both of them spend the same time, and actually the attacker can do even better if they want to. It's kind of a square root. But overall, so this doesn't work, right? So to make this scheme Diffie-Hellman work, you really need the honest parties to do something else. They can't just naively compute the product many times. So the technique we use for this is, and now I'm starting to draw a graph, is to just arrange all these group elements in some circle in this case, and Bob wants to compute this 13th power G. So the naive way of doing this is to just keep multiplying along the outer edge of the circle, and then eventually he ends up there. But of course, multiplying by G twice is the same thing as just multiplying once by G squared, right? So you compute G squared once, that costs you one multiplication, and later you can skip half of the other multiplications. So you can replace all of these pairs of two edges by just one smaller edge that takes you the same time to compute. And you can iterate this and do it again and again, right? And this is exactly what square and multiply does effectively. It takes your original graph, which is like a big circle, and then inserts additional edges by recomputing a little bit of data. These are the powers of G g to the powers of 2. And then you can just take a very short walk in this graph and get anywhere you want. So taking all of these things together, you get something that looks a little bit like this, and that is an example of something that looks a lot like an isogeny graph, and there will be examples of this later. So there's some similarity, and these things work, and they're already used in cryptography, just not with this viewpoint normally. Okay, so that's a big picture idea. Yeah, historically, when we do Diffie-Hellman on groups, this fast mixing requirement is also expressed in the fact that the powers of g to powers of 2 are connecting the graph very well, right? You can find a log-sized path to any node you want just by looking at the binary expansion of your exponent. And we have an exponential difference in the work for the honest user and the attacker. And then, of course, there's this whole quantum thing, so this is what makes things awkward for traditional Diffie-Hellman. Any group you could choose, the attacker can also just run Shor's algorithm to recover the discrete log, so this is broken. But in some cases, for some of these traditional group-based, discrete log-based constructions, we can replace them using isogeny graphs, because they sometimes have a lot of the same structure, and we can just plug in an isogeny graph instead of this square multiply graph, essentially. There's a little footnote here, because this is really not universally true. There are a lot of things that don't easily generalize, and I'll also explain why that is. And this seems to be kind of intimately connected to the reason why Shor's algorithm doesn't apply. So I'll get to that later. Okay, so isogeny graphs, they can look a little bit like this. So we can already see that this left picture is very similar to the square multiply graph I just showed. It's very regular, symmetric. The right picture is extremely random. Actually, the circle shape doesn't mean anything. It's just a random way of arranging the nodes that I picked. But you can see that the connections are pretty irregular and don't seem to make any sense. So the big question, of course, which of these do we want? Maybe we can do a show of hands again, because this is supposed to be interactive. So who thinks that the left graph is very good for post-quantum cryptography? Okay, that's 4 people or something. Who's in favor of the right side? Okay, that's many more people. I also see some people who haven't raised their hands at all, so thanks for your faith in isogenies. Yeah, the answer is both of them. So everybody who raised their hand at one point is actually correct, as it seems. Yeah, they're used for different things, and I'll also get into lots of these different cases a little bit. Okay, so this was like the big picture overview, and now in order to explain what's actually going on, I have to get into the mathy details of this. I'm trying to make it accessible, even if you're not super deep into algebra yet, but I mean, there's a little bit of math in here. But, so please interrupt me at any time. Feel free to ask. I'm here to explain stuff. And I think understanding the basics is probably more important than getting through all the crazy stuff at the end. So I'm happy to spend time on that. Okay, math. I guess, who has seen elliptic curves before? That's almost everyone. That's great. Okay, just for recap and to fix notation, elliptic curves are just algebraic curves defined by a particular shape of equation. There's an abstract mathematical definition, but for the purposes of this talk and for algorithms, we just fix some particular way of writing them down. So yeah, it's a quadratic equation in one variable y, and then there's another term on the right side that's cubic in x. And A and B are in some field. In cryptography, this is a finite field, and there's a little technical condition to make sure that this curve is actually non-singular. Otherwise, things kind of break down, and none of this theory really works. So for an elliptic curve, we require that it's not a singular curve. And then, once we have this equation, we can clearly also talk about solutions to the equation, right? So these are points. And in addition to the points that have x and y coordinates here, we also add another point that's written infinity. If you know projective coordinates, that's where it comes from. That's why it's called infinity, because it's a point at infinity if you take the projective closure of this curve. For practical purposes, you can just think of something that kind of lies outside the x-y coordinate plane. And it's there for technical reasons to make a lot of the things that I'm going to talk about work. Okay, so what's nice about this is that E is an abelian group, so you can have a notion of addition, you can add points, you can subtract them, there's a neutral element that behaves kind of like a zero. And this works mathematically, it's an abelian group. What's also nice is that we can compute this, and that's of course what's been used for decades by now in classical pre-quantum cryptography. Yeah, these formulas are kind of messy, and I don't want you to remember them, but what's interesting is that they're all very explicit, and it's just polynomials. You can dump in some coordinates and you get out a result, and there's very clear and explicit instructions to compute these things. Indeed, the extra point we added, the point at infinity, is the neutral element for this group law. So this is why we needed, I guess, to make everything work, and the inverse is just mirroring on the x-axis. So the geometry of the curve kind of plays into how this is defined. And indeed, a picture that people often show is this. So plotting everything over the reals, you get a curve. This is defined by this equation, x cubed minus x plus 1 equals y squared. And the addition law actually has a very nice geometric interpretation. So it's defined by the criterion that 3 points have 0, or I mean, the point at infinity as their sum, if and only if they're on a straight line. Okay? So it happens to be the case that every straight line intersects the curve in 3 points when you count the multiplicities correctly, and those 3 points must sum to 0. Yeah, and now here's the example why we need this point at infinity. It's kind of there to make things work when you don't actually have 3 points of intersection. So it kind of it's assumed to lie on every straight line that is vertical. Okay, in reality, the picture doesn't really look like this because we do everything over finite fields, and there aren't any nice lines, connected continuous lines over finite fields, so everything becomes discrete. But the picture is kind of the same. It's still symmetric around the x-axis, so you can think about solutions to this equation, and you can plot the points. And what's magical and very useful is that everything still works. So you can still do point addition. You can see here that this line, which is now also like a discrete arrangement of points, still has 3 points that lie on the curve. They're plotted kind of thick in this picture. And everything works the same, really. So that's what we use in cryptography, and what we have been using for a long time. Yeah, so throughout this talk, I'm also inserting these little snippets of Sage. It's a computer algebra system, so the purpose of that is to show, first of all, that everything I'm talking about is not some abstract moon math, but it's really concrete. You can compute with it, you can dump it into your computer, and it outputs something eventually if you wait long enough in some cases. And yeah, so defining an elliptic curve is straightforward. You just take an elliptic curve with your coefficients that make up the curve equation. Okay, so as I already mentioned, and I guess I'm doing this quickly because everybody has seen this, elliptic curve Diffie-Hellman uses exactly these elliptic curves. So you just choose an elliptic curve nicely so that it has safe parameters. And then the key ingredient to making elliptic curve Diffie-Hellman work is to define scalar multiplication, which just means adding a point to itself p times. And just as before, here we don't really want to add it n times in a straightforward way, but we really want to use a square multiply, or double n as it's called now because we have additive notation, but it's the same thing. And then we have this protocol, which is just Diffie-Hellman, but with elliptic curves. Okay, one reason why this slide is here is because this notation, the scalar multiplication map, will show up later again, so keep that in mind. Another subtle thing that confuses people in different ways is that when we talk about points on elliptic curves, we generally, in math, we think of points over arbitrary field extensions, right? So one basic example would be if you again think about a curve over the reals, then you could have points with complex coordinates in them, and that's fine. We just do the algebra as we normally would, and everything works out. And the same thing, of course, happens over finite fields. Mathematicians think of the algebraic closure, and everything becomes kind of easy in that case. But when we do computations, we really want to think about how to write these things down and how to represent them. So that's why it's very important in Isogeny-based cryptography to keep in mind where your points actually live. Is this over like an exponentially big extension or something like that? It could be kind of messy. So we keep track of that, and that's why there's this terminology of just saying a point is defined over some field k, which might just be the base field or a very large extension. And we consider these things to be important. Okay, so again, just a definition and some notation. And then saying a point, for me, means really a point over the algebraic closure. And if we want to speak about points that lie over a specific field, we have this notation, say E of k or something, like with parentheses here. Okay, this will show up every now and then. And in Sage, so this is kind of a contrast between Sage and the abstract math view. Sage only, because it's a computer algebra system, only really works with the field that you specify in the beginning, and you can only talk about points that lie over the base field of the curve. So it changes a little bit how to approach these things, and it also highlights a gap in terminology between math people and more computer science oriented people. But everything can be made to work by using these chain train things, so you can always move back and forth between different fields and make everything work in the end. Okay, so that's recap for most people, I hope. Elliptic curves, you've seen them. So what are isogenies? And this is a complicated word for something that's actually pretty natural, and I'm hoping to convince you of that. So isogenies are just nice maps. And I'll mention shortly what that means, but it's really just the obvious correct notion of a map between two elliptic curves. Right? So when you have an algebraic structure, you can think about what kind of maps between these things exist and what properties they should have, and isogenies are the answer to that when you talk about elliptic curves. So concretely, what does that mean? An isogeny is a non-zero map. That's added for technical reasons, so there's only one zero map. You just exclude one of these things. And it's supposed to be a map between these elliptic curves that's given by rational functions. Right? So this mirrors the fact that elliptic curves are algebraic curves. And we just demand that the maps between them are also defined by polynomials. And they're also supposed to be group homomorphism, which mirrors the fact that elliptic curves have a group structure, so you want the maps between them to also respect that structure. Right? So it's just a map that respects both of the major structural aspects of elliptic curves. Yeah, just for recap, rational functions means fractions of polynomials, and group homomorphisms are defined by the fact that you can exchange them with the loss of the group in this case. Associated to an isogeny, which is this nice kind of map, you can always consider some data. So one of the most important invariants of an isogeny is its kernel, which is just defined as a group theory. So it's the set of points that get mapped to the neutral element, the point of infinity. And for the purposes of this talk, pretty much, we also talk about the degree a lot, which is more or less the size of the kernel. It's not exactly true. There are some cases where this doesn't hold, but that's what the little asterisk is here for, and you shouldn't worry about it. It's morally true almost always, and there's like one weird case where you have to think about it a little bit more. Okay, so in some sense this kind of encodes how big the isogeny is. It's kind of a measure of the algebraic complexity of the thing. How much space do you need to write it down? Okay, examples. So these examples are selected so that they all highlight different aspects of what isogenies can be, and there's different types of isogenies. So the first example is really just a generic isogeny between two distinct elliptic curves. So we're working over a finite field here, F71, and the isogeny is defined by explicit polynomials of this shape. Right? So you have a fraction of polynomials in x and y. And you can verify by plugging in these formulas into, I never remember which side of this, but one of these two equations, that this actually defines a well-defined map between the curves. When you plug in a point on one, you get a point on the other. And by convention, we're kind of saying that whenever the denominator here vanishes, then the result is the point at infinity. So dividing by zero gives you infinity. That's again kind of a hacky way of saying something that's easier or like more natural to phrase in projective geometry, but that adds one coordinate and the slides are kind of small, so I decided to keep it smaller. So indeed, you have these denominators, and there's x minus 2, powers of x minus 2 in the denominators, which means that the points that get mapped to infinity under this map are points with x coordinate 2. And there's 2 of those, I wrote them down here. And of course, the kernel also contains the point at infinity by definition. It's a group homomorphism, so it should preserve the neutral element. Okay. And that makes it degree 3, because there's 3 points in the kernel in this case. In addition to these general random-looking isogenies, many curves also have more special isogenies associated to them. And this is an example of one such thing. So here we just look at a general elliptic curve y squared equals x cubed plus ax plus b. It's the general form, and then we can look at the map that takes x to minus x and y to square root of minus 1 times y. So this is an example where you might need to extend the base field to get the square root of minus 1. And then again, you can verify that this maps it to this other curve. And well, yeah, because there's no denominators here and there's no way to get infinity. The only point in the kernel is the point at infinity itself, which means that this map is actually an isomorphism. So it's just a change of coordinates, if you want. It's kind of the same curve in some sense. Okay, and then there's another isogeny that we've already seen, actually. Okay? So this is the multiplication by m map that shows up in the elliptic curve diffie and it's just adding a point to itself m times, where m is some integer. And this exists on any of these elliptic curves, so it's obvious that you can compute this. You can take an m-fold multiple of a point. What's slightly less obvious, perhaps, is that this is really an isogeny. So why is that? Well, on the slide for elliptic curves, I showed these formulas for adding points, right? And these are like combinations of polynomials. So that takes care of the first part of the definition here. It's clearly a group homomorphism. This is true for any group. And the first part is fulfilled because the addition formulas are actually algebraic. They're polynomials, so composing them gives you more polynomials. And now something that's definitely less obvious is that the degree of this isogeny is m squared. So there should be m squared points in the kernel, except for like weird cases. And in fact, we can say even more. So there's this notation of E brackets m, which is the kernel of multiplication by m. So those are points whose multiple by m is 0. And yeah, the structure of this group is just a product of two cyclic groups. Right? In some sense, it's a two-dimensional space. If m is prime, it's really like a vector space. And so you can identify all the points who get killed by the multiplication by m with a two-dimensional thing. And this is also something that kind of shows up in a lot of isogeny-based algorithms and protocols. So yeah, you should keep that in mind. And finally, that's the last example. There's over finite fields. There's another type of isogeny, which is very special, and it's just Frobenius, right? So the Frobenius map exists on finite fields, or in characteristic P generally, and the Frobenius endomorphism of an elliptic curve defined over fq is just defined by taking the qth power of both coordinates. So taking the qth power of the curve coefficients is supposed to fix them, because the curve is defined over fq, and the coordinates kind of can change. Right? So you have points over extension fields, and they get mapped to something else by this map. Yeah, one reason why this map is very interesting is because the kernel of taking that -1 is actually just a set of rational points. So this is kind of subtle if you haven't seen this before, but the point is that the points fixed by Frobenius are the rational points that are actually have both coordinates in fq, and then taking that map -1 means we're looking for the points where pi acts as the identity. And this shows up in point counting algorithms, and it's kind of a cute, interesting thing. Yeah. What's more important for the applications that I'll show is that an isogeny is fq rational, so it has all the coefficients in these polynomials in fq, if and only if you can swap it with, or it commutes with Frobenius. Okay, so this shows up in a lot of proofs for example, C-side, which I'll talk about in a little while. Okay, so here's another explicit example of this in Sage. You can take curves, you can define them, and then as of recently, this has actually been revamped quite a bit by people like me recently. You can define the scale multiplication map on this elliptic curve. So mu here is really like an isogeny. It's not just a Python function that computes the multiple, but it's a proper isogeny. And yeah, if you print it, it outputs this information about itself. And then you can do all kinds of things to it. You could evaluate it, you can compose them with other isogenies, but you can also just return the rational maps and output this formula. Yeah. Okay. Are there any questions about isogenies in general at this point? Is everybody still following? Who's lost me? Who have I lost already? 0 people, allegedly, so that's that's good. Okay. So, just to paint a little bit more of a picture of what isogenies can do. So I've shown some examples, and it sounds like there's tons of these isogeny thingies. But it's actually the case that besides the obvious isogenies that every curve has, having isogenies between distinct curves is actually fairly rare. So if you just write down 2 random elliptic curves over a finite field, they're probably not isogenous. Okay, so that's why we have this concept of being isogenous. It just means that there's any isogeny between the 2 curves. This again is part of the reason why we had excluded the 0 map, because otherwise you could always just have an isogeny that maps everything to 0. But excluding that, it's actually quite rare that you can find an isogeny. If you do, though, the isogeny comes with a backwards isogeny in the opposite direction. So they come in pairs. Every isogeny has a dual isogeny. It's written with this little hat. And it's defined by the fact that composing the isogeny with its dual gives you the multiplication map by the degree. Okay, so one way to memorize this or to understand what's going on here is that this is almost the definition of an inverse, but instead of getting 1 when you compose them, you're just getting the degree. And that's the best you can do. You can't really divide this out. There's no inverses in general because these things have a non-trivial kernel, so they're not injective. But once you admit that the composition can be a multiplication map by the degree, then you can always find this isogeny. It always exists and it's unique. One more thing about this relation of being isogynous is that over finite fields, it's very easy to test this just by computing the number of points on the curve. So two curves are connected by some isogeny if they have the same number of points over that field. So this is a very interesting theorem. This also holds more generally. Okay. And extremely non-obvious fact is that you can compute the number of points without writing them all down. So this is a very interesting and very nice algorithm. It's polynomial time, SEA algorithm. Which means the bottom line of this slide, which has a bunch of random facts, is that this relationship of being isogynous is an equivalence relation. So it's symmetric and reflexive and so on. And it's easy to test this. So this is sometimes nice for when you do isogeny-based protocols and you want to check that the input is actually valid. You can just test it easily by counting points. Otherwise, somebody might be able to fool you by giving you bad inputs, and then you have to think about how to detect that or if it leaks anything interesting. But this is all easy, so it's easy to test that. Computationally, I haven't said much about how to find isogenies, right? So I said that they are kind of rare, so you wouldn't find them by chance. But then how do we construct them? And that's the purpose of this slide, which is a very, it's kind of the main theorem of isogeny-based cryptography, if you want, so this is very important. And what it says is that to choose an isogeny, it suffices to essentially just pick a finite subgroup of your curve. Right? So pick a bunch of points, they have finite order because you're in a finite field, and then that defines an isogeny. And this isogeny is defined by the property that its kernel is just that subgroup. So it's a little bit like taking a quotient group or something, which is why we use that notation. You could abstractly always talk about this quotient group, of course, just by working with cosets of points. But what's interesting and not obvious here is that this quotient group actually is realized as another elliptic curve. Right? So that's the non-obvious fact. And this other elliptic curve can be computed along with the isogeny when you have the kernel. And just for practical reasons, it's important to point out that nothing happens over extension fields here. Yeah? You have a curve over some field, you have points over that field, and then the isogeny and the codomain curve will also be defined over the same field. Alright, so practically in isogeny-based cryptography, if we want to choose a random isogeny, which could be a secret in most cases, it suffices to just choose a finite subgroup, and that defines an isogeny. In practice, of course, we want to compute these things as well, because the classical isogeny-based setting is that isogenies are secrets, the codomains are public, so we have to have some way of computing these things, actually. And they exist. The old version is due to Jacques Ellul from the 70s, in fact, so this is very old. But the important point is that these formulas basically have to enumerate the entire kernel, so you have to have small kernels for this to work, otherwise it just takes forever. So the solution for this problem is that in all reasonable isogeny-based constructions, we take many small steps of this kind. Right? So you repeatedly choose a small kernel subgroup, big enough so that there's a bunch of choices, and then we just take the composition of all these steps. And because isogenies are well-behaved under composition, that is still an isogeny, and it can be quite large. The degree is multiplicative, so it gives us potentially an exponentially large isogeny in the sense of the degree, with only a linear number of steps. And that's exactly what we want for cryptography. Right? So one way of viewing this type of taking small steps one at a time is to walk around in an isogeny graph. And isogeny graphs are the things we have already seen, and I'll formally define them in a moment. So just again to show that this is all very explicit, Sage Math has implementations of these isogeny formulas, in fact for more general cases as well by now. And the way you use it is just by picking a bunch of points on your curve that generate a finite subgroup, and then dumping them into this isogeny command, which computes an isogeny, and this object can be used to evaluate them, and find the codomain, and so on. And indeed here, so we've chosen an isogeny with kernel k, that's a point of order 7 on this random curve here. And we can plug that into the isogeny, and we see that the result is the point at infinity. That's the notation that Sage uses for this. So it's indeed in the kernel, and we can also use these objects to compute like more data about the isogeny, find the rational maps, find the codomain, do all of these things. It's very explicit. And of course, if you try to do this on a large composition of small degree isogenies, it will just never finish because this expression is actually exponentially big in that case. But for small cases, we can use this and we can play around with it, and it's a very useful tool. Okay, so I was mentioning this random walking on isogeny graphs. So what is it? It's basically just the idea of taking a graph where the nodes are elliptic curves and the edges are isogenies between them. And so it's based on this isogeny relation, except that in order to make this more useful for cryptographic purposes, we usually restrict to particular types of isogenies. So to do that, we choose a set of primes. These are going to be degrees of isogenies. And then we define the isogeny graph with respect to this set of primes, prime degrees, just by saying the vertices are all the elliptic curves over our base field, which will be a finite field in the usual case. And the edges are given by the L isogenies, where L is a prime in this set S. And again, just over K, because we want everything to be computationally easy over the actual base field. And then, well, because there's lots of redundant representations of everything, we take everything up to K isomorphism. So among all the actually identical but different looking curves, we just pick one representative for every isomorphism class, and then we have to accordingly identify things on the level of edges as well, so that we don't have tons of duplicate edges. Yeah, and if you do these definitions and you plug in various choices of base fields and degrees S, you get these graphs that I already showed in the beginning. And the core distinction here in the typical case is that if you use a prime field, so just Fp with P prime, you get this kind of structure. And if you use a quadratic extension of, well, the prime field in this case, actually more generally, you get this more random looking structure. Yeah. This is not always true. There are other, this is one particular example, but in the cases that we care about in cryptography, this is the general picture, and that's the big distinction between what kind of isogenies you work with. Okay, so yeah, I just said that this is a special case, and the special case is what I will explain right now. So in general, elliptic curves can be kind of annoying computationally because it's difficult to actually work with points of arbitrary order. It's hard to find it seems hard to find a curve that has like a prescribed order in general. If you also want some other properties that we want for isogeny-based cryptography. So it's kind of a tricky issue to find good curves to work with. And one example is why we want that is because if you want to write down points of order L, where L is some prime, in general for a random curve you would really have to go to large extension fields of degree approximately L or even L squared in some cases to find these points. So we want to construct examples where this is better and easier, and the solution lies in supersingular elliptic curves, which is something that's considered sort of weird by mathematicians historically, which is why it's called supersingular. So this has nothing to do with singular curves, by the way, right? These are still non-singular curves. Supersingular just means like super crazy, special, different. It's not great terminology. I'm also not a fan of the word isogeny or this word. There's a lot of historical choices that I would do differently, but it is what it is. The opposite of supersingular is called ordinary, by the way, which is quite reasonable. So some people just call them non-ordinary. Okay. Point being, these supersingular elliptic curves are, practically speaking, a way to control the number of points on your curve. Right? So for a supersingular curve, it's always a priori clear what the number of points is. You don't have to do crazy point counting methods. You just check, is it supersingular? Yes, and then you can, in many cases, already exactly write down the number of points, or you can at least narrow it down quite precisely. So this is the special case that we care about in isogeny-based cryptography. We have a large prime P, and then taking a supersingular curve means that we have exactly P plus 1 points over Fp. And indeed, we can say more about the group structure if you look at the actual structure of the group of points. So this kind of relates to what I talked about earlier when I had this E bracket M notation. So if you look at the set of points over Fp, then it's really just a cyclic group in this case. And if you go to a quadratic extension, you get a second cyclic vector. So it really turns into like a very regular, easy structure. It's just a two-dimensional thing. They can be spanned by 2 points. And these 2 points can form a basis. Every point has a unique representation as a linear combination of these 2 points. So it's all very neat and clear and easy. And we like this a lot for isogeny-based cryptography because it allows us to choose nice groups and we don't have to worry about annoying things like having to distinguish where our points live in which extension, how large do we have to choose things. We just think about it ahead of time, we fix our choices for P, and then in the ideal case everything works out using just the choices we made and we don't have to do anything else. Okay, so that's why until the lunch break, not to be confused with the coffee break, all curves will be super simple. I won't talk about ordinary curves anymore. If anybody's interested in ordinary curves, this can also be a thing in isogeny-based cryptography. I'm happy to talk about that later. But yeah, for the purposes of this talk, it will just be super simple. Okay, so elliptic curves and isogenies, that was a lot of math all at once, and I hope it will maybe be clearer after I talk about some of the applications. Yeah, now would be a great time to ask more questions if you have any confusion, or if you want me to go back and look at the slide again. Now's a great time for that.
So the question is, I was thinking about these, like the degrees of these isogenies. You said the degree grows multiplicatively, so you get back a high degree isogenies.
Yes.
And so does that mean, that means you, in the end, have a curve with relatively quite fewer points than the curve you started with?
No. So the number of points is actually the same. That's what Tate's theorem says. It was on one of the slides. The reason is that the isogeny is not surjective on rational numbers.
Oh.
So there's points that lie outside the image if you just look over Fp, or F, whatever your base field is.
You said that you look at the curves up to some isomorphism. So is it easy to compute the one representative for these curves?
Yes. So over the algebraic closure, there's the J invariant, which is an easy to compute numerical invariant, and that's just an isomorphism invariant. So it tells you exactly 2 curves are isomorphic if and only if they have the same J invariant, and that's an easy formula. For these isogeny graphs, you actually have to be a bit more careful because it's not over the algebraic closure, it's over a fixed base field, and we want isomorphism over that field. So it's a little bit more subtle, but it's still something that's easy to work around. In some cases, there's a unique representative even. For C-side, for example, this is the case if you choose a particular type of curve, there's only one of them for every isomorphism class. And in general, it's a non-issue, it's something that we can do. Okay, so if there's no more questions at this point, then I can show the first very easy application of this. And it's a hash function. It's due to Charles, Gorin, and Lauper. And the idea is really simple. I only have one slide about this because it's so straightforward once you've done all the math. So the idea here is that this is an isogeny graph, this picture, and you just label edges, which are isogenies, in an arbitrary way using zeros and ones. It should just be deterministic. And then when you have your input to the hash function, you compute the hash value by just looking at every bit of the input and deciding which of the 2 edges to take at each step. Okay, so more formally, you have a starting curve, some fixed thing that the designer chose in advance, and then you're walking around on this graph, so at any point in time you're on one of these elliptic curves, the dots are elliptic curves, okay? And you start here, and you process your input, and you just choose one of the outgoing isogenies at each step. And the hash value in the end is some identification value of the curve that you end up on. Okay. So that's pretty much it, and it's not overly hard to see that, for example, finding a pre-image to this hash function corresponds to finding a path between the starting curve that everybody has agreed on and the hash value. It's a little bit subtle because there might be more edges than the ones that they're actually using, so it's not exactly pathfinding, but it's sort of the same thing as pathfinding with extra constraints. So it might actually be harder than just pathfinding. And collision resistance also, finding a collision boils down to essentially finding two distinct paths, right? And now since, as I mentioned earlier, these graphs are actually symmetric, so or undirected, finding two distinct paths boils down to essentially finding a cycle. So cycle finding in isogeny graphs is kind of what the collision resistance of this hash function relates to. So that's kind of I guess it gives some intuition why these graphs are interesting and why they can do crypto. There's a lot more subtleties to all this, but I won't get into that. Okay, so that's the CGL hash function. It's very straightforward once you've done all the math to get the isogeny graphs. And yeah, so if we wanted to have a break after half, I guess now would be a good time. And it's probably not going to be half because I have too many things to talk about. So yeah, I guess we can continue in like 3 minutes or something. That's all right. Okay, so isogenies, we've seen them. There's a basic example, but hash functions aren't really generally what we go through all this hassle for. There's easier ways to get hash functions that seem secure. So now I want to talk about some things that can only be done with isogenies, or can only be reasonably done with isogenies, or seem to be a good application of that. And the first example of that is what we call seaside. So don't get misled by the spelling here. The pronunciation is seaside, not C-S-I-D-H. Yeah, it was invented or started at a research retreat in Tenerife, which is where this picture was taken, by a group of people, including myself, and Wouter Kastrik, Tanja Lange, Chloe Martinel, and Joost Lorenz. What it does is, it's essentially a version of Diffie-Hellman that works in a post-quantum setting. So how do we get that? Well, the high-level view of this isogeny-based key exchange is sort of the same as for normal Diffie-Hellman. You just have secrets, and then you exchange something, and then you have more secrets, and you get a shared secret. So concretely, in this case, the secrets are isogenies. So there's a shared starting curve, usually called E or E0. And then Alice and Bob, they're color coding, by the way, so red and green stands for Alice and Bob. They both just choose some isogeny in a way that I'll get into in a minute. And using these isogenies, they are kind of walking around on the isogeny graph, and they get a public curve. That's the end of their isogeny. And then they exchange that, just like in classical Diffie-Hellman, they exchange their powers of the generator. And then, they exchange it, and then they should somehow find more isogenies from the other party's public curve, such that the endpoint of both of these isogenies on both Alice and Bob's side ends up being the same. And that should be our shared secret. And so we're kind of doing the normal Diffie-Hellman thing, but we're replacing group elements by curves and exponents by isogenies. So it's all like ramping it up to more complicated math objects. And the big issue, of course, is how do we find these parallel isogenies, right? If Alice and Bob just do random things on each side, they just end up on a random spot, and it's never going to be a shared secret. So how do we find these parallel isogenies? And the way Seaside does this is to essentially define a particular type of isogeny that's special in such a sense that you can transport it to other curves without actually knowing what the connection between these other curves are. And it's kind of the same isogeny in a well-defined sense, and that's what makes the square work in the end. What are these special isogenies? In general, this is kind of complicated to write down, but in the particular case of Seaside, there's actually a very nice, easy description of this. So here we have a supersingular curve defined over Fp. Supersingular means there's p plus 1 points, and it's a singular group. So for every prime divisor of this group order, by group theory, there's a unique order L subgroup. So this is like Lorenz theorem, I think. And you can compute this unique subgroup just by finding a generator of the entire group. It's easy to do all of that if you have the factorization of p plus 1. And then it's easy to find an element that generates this subgroup HL. So it's a point of order L that's rational over Fp. So both coordinates in Fp. And then we just take this subgroup that's special, and it kind of really comes from the structure of the algebra in play here. It's not something we choose arbitrarily, but it's like really a well-defined thing. And we just use that as the kernel of an isogeny. So that's just running the normal formulas with that subgroup that we found, and it gives us an isogeny. And these isogenies are the ones that I call special in the context of C-set. Okay, so unique special subgroup of order L, and then we just take the isogeny from that. And now the magic happens when you start considering how these special isogenies behave and how they interact. So there's two things to consider here. The first is what happens if we just keep doing it. Okay, we just keep picking the special isogeny, we walk around on this graph. What happens? And generically, the picture looks a little bit like this. Right? So you start from one particular curve E, and then you just take your special steps, and they're all easily findable and uniquely defined. And eventually you have to cycle back because it's over Fp, it's a finite set. So there has to be some kind of cycle of this shape. And then once you're there, you keep cycling because at this point the next step is deterministic again. So it has to be the next curve again, and then you're in the cycle. And what's interesting about this is that we can actually show that this tail can't exist. And that's because every curve only has degree 2. I mean, as a node in this graph, it only has 2 outgoing edges. And so you can't have a setting where there's 2 incoming errors from one curve, because one of the errors is already the outcome one. So this tail can't really exist, and you really have a cycle. If you keep repeating this construction, you end up on the same curve. So we have these cycle structures from special isogenies. And then the other question is, I defined this for arbitrary L's, right? And having one big cycle doesn't really help. This is kind of like the example in the very beginning of computing an exponentiation. This will be easy to revert. So we need more connecting edges between these things. And therefore it's good to consider multiple L's. And now the question is, if you have multiple L's, how do the isogenies defined by these special subgroups for each of the L's interact? How do they compose? So generally now we're considering 2 primes L and M, just like before. They're divisors of p+1, and so they give rise to these special isogenies. And if you do one and then the next, like you first do the L step and then the M step, you end up on some curve, and you can also consider the case where you do them in the opposite order. And so you first do the M step and then the L step, and in general you would expect that this gives you different things. You just end up on different curves because they're different isogenies. However, we can prove, and this is also a fun exercise, that actually the kernels of both of these compositions here are the same, and they're just the group generated by the kernel of this together with this. Yeah, you can try figuring this out later, or we can talk about it in the lunch break. So what this means is because of the unique association of isogeny kernels with isogenies, the order can't really matter. It's actually the same isogeny, more or less, up to like insignificant choices. Okay, so that's why the L and M are now merged together in this notation. There's no more specified order to it. And you actually get this kind of parallelogram, and it really maps you to the same curve, no matter which order you do stuff in. Okay, and yeah, I'll show you in a second what this entails in the end, but just to show the C-side construction in one slide, as we specified it in 2018. So to make C-side, you just choose a bunch of primes, L1 through Ln, so these play the role of these special isogeny degrees now. And then you want to make sure that P of this special form is a prime number, so if it's not, you just pick different L's and try again. And then we look at curves with this particular special shape, so this is a slightly different form than what I showed in the beginning. It's an untwisted Montgomery curve, if you want. This is convenient for some reasons, but the important part is that we look at supersingular curves, so that gives us the nice group structure, it makes the special isogenies happen. And then we just look at all of these special Li isogenies, right? So the Li's were chosen specifically so that we can do this. And then we get exactly this structure. And this is really a consequence of the 2 properties I just showed, right? Like every individual Li chain has to be a cycle, and they have to compose in this nice way because the order can't matter, so that means every red step is always the same number of blue steps. And the colors here encode the different Li's. So you get really this nice, pretty structure, and it looks a lot like the square and multiply graph from the beginning, except that it doesn't come from a group, so we can hope that it has stronger cryptographic properties or something, which will be true, and I show that in a minute as well. Yeah, and also, as a consequence of some of these choices that we made here, we can easily walk around on this graph, and it's easy to just take a step and orient yourself and know where you are and how to continue in the right direction. So having all that, how do we make a key exchange? Well, essentially we do kind of the same thing as for the square and multiply case. You just pick a path in some well-defined sense, and then we execute the path, we exchange our endpoints, we execute the path again, and then hopefully by the structure of this thing we should end up on the same end node, which is a curve. So we have our starting node here at the top. Both Alice and Bob agree that they start on this curve, and then Alice and Bob both choose their secret paths here. So plus and minus are just arbitrary labels for the directions on this on these cycles. It doesn't really matter which one's which. And then they start walking. And they can do this because it's all efficient, explicit, computable. And so they walk around on this graph. They just follow the instructions that they chose ahead of time. And then, well, Alice ends up here after she finished her instructions. Bob ends up here, and they exchange labels of this node. So they just exchange like the coefficients in the curve equation, or in the particular case of this is capital A. And then they do it all again in accordance with how Diffie-Hellman generally works. So they just follow the same instructions. And because of all the magic that went into this, they actually end up on the same node. And now they can take the coefficients of this curve and hash it and use it as a Chern secret or something, just like for normal Diffie-Hellman. Okay, so this is my one magic trick I have in the talk. This actually works. Right, so this is, you can already do this and it's fine, but there's a more conceptual way of figuring what's going on here, and this is what I want to show now. So based on the fact that these cycles are compatible, the order doesn't matter, you actually only need to count how many steps you did in each direction. So you, instead of keeping track of this plus, plus, minus, and so on, you just count how many pluses and minuses do I have in total, and because things have to cancel because of this compatibility, it's enough to just count how many steps of each color or each Li. Another way of phrasing this is that there's actually a group action of additive vectors. Right? So these are like exponent vectors. They count how many steps of each Li, and because of this compatibility, you can actually compute the action. Like you can, if you add vectors here, it corresponds to just executing them one after another, which is just the thing you want for a group action. Moreover, the group here is infinite. Integer vectors, there's infinitely many of them. But the set of curves is finite because it's all over a finite field. So there has to be some kind of non-trivial kernel of this action. The action cannot be free. Right? There have to be vectors which act trivially. They don't do anything. They must exist. They also need to be full rank because the quotient has to be finite. So you actually get a lattice. Not the kind we use for cryptography, but it's also, it really is a lattice. And it lives in the CN, and it consists of all the vectors that act trivially. And of course you can also add and subtract them from your secret keys, and they don't change anything because their action is trivial. And indeed, this is not some random lattice that no one understands, but we can mathematically argue what this should be, and it ends up being exactly the ideal class group of, in this case, C adjoint square root minus p. So this is like a quadratic number field, or an order in a quadratic number field. And we can technically compute these things. It's not particularly efficient, but there's ways of arguing about what this structure is. And indeed, for example, we get an estimate for the size, which is very good and helpful for cryptography. Yeah. And one takeaway, so I mean, there's a bit of scary math here, but one takeaway from this slide is that we have a group that's abstractly defined. It's like an algebraic object, and this group really tells us when two paths go to the same curve. So we have a huge exponentially sized graph. You can't really write down the entire graph, but you have this abstract group that you can somehow compute in some case, I mean, up to some limits, and that tells you exactly when two paths will lead to the same curve. And you can also use this to reduce things and make large exponent vectors smaller because you know what X trivial.
So, I'm sorry, when I want to compute a basis of this lattice, what would be the complexity as a function of n?
So this is like an L1/2 type thing. It's like an index calculus algorithm. Yeah, classically. And quantumly, finding a basis is polynomial time, but having a basis is not necessarily useful for some of the things you want to do, and then you still have lattice problems, actually. So you end up, if you want to solve CDP or something, having a basis doesn't help you, right? You need a good one.
To which n can you do it, or to which p? What's the record?
The current record is p of 510 bits.
Should we satisfy 1/2?
Yeah, and but those are the sizes where a lot of people think that it's not enough for post-quantum security. So it's definitely enough for classical attacks, and the quantum security picture is a bit messy.
So then 1024 would be out of reach.
I'm not sure if anybody has tried actually. It seems conceivable that it could be doable if you try hard enough. But this 510-bit computation was already pretty big. They did that on a cluster over a couple of weeks, I think.
So I still don't quite follow why the mapping of the curves is working efficiently for longer time. So my understanding is the L's are essentially the sizes of the jumps that you can make on this graph, right? The factors of p minus 1.
Sizes, I mean, yeah, that's the size of the, or like it's essentially the complexity of computing a step, yeah, and they're very small.
Yeah, and so these are, well, my understanding would be that that P is larger than the largest of these values by probably a exponentially sized factor or something that is not reachable. So if I want to get to a decently far away point, don't I need, since I cannot just double up or like, since I can't do square multiply on these jumps, how do I get exponentially far away?
Yeah, that's a good point. So the answer is that there are many L's. So at every time you're on one curve, you basically have you have two directions, and you have, let's say, in the particular instance that we've considered at the beginning, you have 74 different L's. So you can just count how many exponent vectors are there. Well, if you take, let's say you just do one step of each L, then you have 2 to the 74. And then if you take multiple steps, you can also count how many exponent vectors
there are. Because I would have thought these are, at least in the, I know these are very small depictions, but they are very massive overlap.
Yeah, there will be duplicates.
And they are few enough for this to not be a problem?
Heuristically, yes. So I mean, once you have this structure, it gets easier to reason about how many of the exponent vectors you're actually sampling for your crypto system end up being redundant. On average, it looks like this lattice is kind of reasonably random, and then it's a non-issue again. It's like maybe a few bits or something. It's not going to massively change the picture.
You need enough steps that you're random in the space, right? So is there a heuristic when you arrive there?
Yeah, I mean, the heuristic argument is just counting. So we have an estimate for the number of nodes. That's approximately square root of p in this case. So it's exponential in log p, that's nice. And then we just take enough steps so that the number of exponent vectors is kind of the same magnitude. And since the lattice of relations here is kind of random, except for like one really weird vector in there, it looks like that's fine. But technically it's open, yeah, it's a heuristic. No one quite knows how much you can prove about this. I guess that some things come from the fact that it has been proven that this graph is an expander. So there can't be too many weird things happening. It has to be sort of random, or like well connected and kind of random, but I don't know what exactly that gives. And also, I think this result is extremely asymptotic, so yeah, it's kind of unclear. But practically it seems fine. I mean, we did experiments on small cases when we figured this out, and it seemed okay. Okay, so concretely, walking around, when we've decided how much to walk around, I claimed that it was easy and efficient, so I just want to show how that works and point out the fact that it's really straightforward. So we need to compute these isogenies with these special subgroups. To do that, we need to find the special subgroups. Well, I'll show in a second how to do that, but basically computing a step in one of these directions, which I would call plus, we just have to find a particular point on the curve of order Li, where Li is one of these special choices, such that both coordinates lie in FP, so it's a rational point, and then we compute the isogeny with that kernel. So it's known formulas, and it's just finding a point with this property. Computing a step in the opposite direction, so this would be like the dual isogeny, is the same thing, but now instead of having both coordinates in FP, you only have the x coordinate in FP and the y coordinate not in FP. It also means it's necessarily an FP squared because it's defined by a quadratic equation, but we don't really care about that so much. But otherwise it's the same, right? So this is a very easy thing. Just for completeness, to find a point of a given order, it's enough to actually just pick random points on the curve, and they're likely to have very large orders, so you can multiply out the parts you don't want from the order, and then you either get infinity or a point of order Li as desired. Then you just have to take care of this y coordinate condition for it to be correct. So this is so easy that we can actually do this in a couple lines of Sage. And here I'm showing how to compute a point that has that is rational. So we work over FP squared here for simplicity, and we get the point, and then we can actually compute the order of this point. So in this case, it's 2 times 3 times 7, and we want to, let's say, compute a 7 isogeny step for Li equals 7. So that means we have to multiply out the parts we don't want, 2 times 3 times that point. So that point that goes into the isogeny computation here is now a point of order 7, and then we get a new curve from that. So this is really all it takes to compute one step on this graph. Very straightforward. There's tons of optimizations to do this more efficiently, especially if you have multiple steps to perform and so on, but the basic idea is very, very easy. One thing that shows up here is that we work over a quadratic extension, which is kind of inconvenient for computations. So I briefly point out that the classical idea of x-only arithmetic for elliptic curves, so throwing away the y-coordinate, working only with x, also works here. And that is because, clearly negation commutes with scalar multiples, and inverses have the same x-coordinate. So as long as you don't care about if you have plus p or minus p, which is the case for isogeny computation, you can just work with the x-coordinate only. And for C-side, this means that you can actually do everything over FP. There's no need for an expansion field to ever show up in the implementation. And that makes it pretty nice. It says relatively efficient here because it's still extremely slow compared to many other post-quantum constructions. But it's better than it could be. Okay, one thing that I haven't yet talked about is why the Shor approach doesn't break this, right? I mean, it looks very similar to normal Diffie-Hellman. We have the same type of graph structure. Like, why doesn't this just break it? And the reason is that, well, depending on who you ask to write down Shor's algorithm, they give you different explanations, but a pretty high-level view of it is that Shor computes this discrete logarithm by defining a particular map from integer vectors of x2 to the group. And this map is defined by taking a power of g, the generator, and h, the public key, and multiplying them together. And then you can see that, for example, the vector minus alpha comma 1 lies in the kernel of this. Because h is g to the alpha, and this turns out to be 1 in the end. For group actions in general, we don't have this multiplication. It just doesn't, it's not a thing. It doesn't mean anything. Okay? So in a group action now, the exponentiation gets replaced by computing an action of an element on, of a group element on of an element of the set. But we can't really make sense of this multiplication, so there's nothing to replace it with in order to attack group actions. And that's the entire reason why it seems like Shor's algorithm doesn't apply here. Okay, so that's C-side. That's non-interactive key exchange. One detail that I haven't mentioned about this is that this non-interactive key exchange is really special in the sense that most post-quantum key exchange schemes are chems. So the difference is that for a chem, one party has to craft a key exchange message specifically for the recipient. So you encapsulate for someone's public key. And in this non-interactive key exchange setting, it's different. You take two public keys. You don't have to know in advance who you communicate with, and they define the shared secret jointly. So this is more powerful for some types of applications. And this is kind of difficult to get post-quantum. Okay. Questions? Yes?
Just quickly go back to the stack ratio and how it's involved.
With the graph, you mean?
Yes.
Here.
Yeah. So my question is, like, what sort of complexity or security do we have here?
I was going to get into that right now.
Oh, okay.
It's the next part. I hope it's on the slide, actually. Oh, I think I didn't talk about. I didn't add that here, did I? Okay. Yeah, the story is. I can get into that briefly, but there's no slide for it. Sorry. So classically, you obviously have brute force graph search. You just walk around and you can do like a meet in the middle type of thing to find a connecting path. So that ends up being like square root of the graph size, which is 4th root of p, more or less. And quantumly, there's an algorithm due to Kuperberg, which breaks a hidden shift problem in abelian groups, and that's exactly what this is, pretty much. And in that case, the complexity is sub-exponential, so it's L1/2, meaning it's kind of the same complexity as classical class group computation, but now you can recover keys. And yeah, you can imagine that as being something like taking a square root in the exponent. So it's like x of square root of log p, more or less, with the confidence interval. An exponential would just be x of log p, so the square root changes it. So there's no nothing faster than Kuperberg's quantum algorithm, as far as you know. And classically, it seems like you just have to brute force it pretty much.
Is that fine for you? So there's a sub-exponential algorithm?
I think they haven't said anything about it. I mean, people are still using RSA, which is classically more broken than Seaside is quantumly, according to this.
Sure.
It's like L1/3, so it's like.
Yeah.
I think it's fine. It's just the debate is about how big the parameters need to be. Clearly, you can scale it up enough to make it safe, and people can't agree on how big it has to be.
So I mean, like, if you go one more slide back. Oh, okay. Okay, one slide ahead. Okay, basically, I mean, Bob does his movements on the graph, and then he comes to his endpoint. So if someone is able to find another set of 4 movements that result in the same endpoint, they basically break security, right?
Yes.
Because he shares his endpoint. So I mean, from this perspective, it looks easy. Is it because the parameters are very small?
Yeah, this is a toy example. I mean, in reality, you have 2 to the 250 nodes here.
150, yeah.
So that's more than you could ever possibly write down.
Because I mean, it's like find a big jump to the end node and like try and jump back and forth and hopefully.
I mean, that's basically the obvious approach to attack this is to just take the starting curve and your public key and start random walking from both of them and see if the trees meet at some point. And then you get like a square root type complexity. It also uses a lot of memory, so there's better ways of doing it if you don't have a lot of memory. There's a lot of stuff going on here, but the basic idea is really just brute force search. Can't do better.
What kind of graphs are you after? Because I would like newer version of
Okay.
graphs that you want to
I personally don't really think about these distinctions. Well, what you clearly need for crypto is that it mixes quickly enough so that you can take like a polynomially long walk and then end up on something that's fairly random. I don't know exactly what graph theory properties you need to get that. I have co-authors who know that. Okay, any other questions on this yet?
What happens performance-wise if you, let's say, take some serious security buffer? I mean, there were discussions about the exact parameters.
Well, it gets pretty bad. I don't know exactly what the scaling of the complexity is, but I mean the smallest conceivable classically secure parameters, which is the 510 bits or 512, is already on the scale of like a couple tens of milliseconds per full secret key operation. So you have to do it twice per key exchange, or at least once. And I don't remember the numbers for the bigger ones, but it got pretty bad. I'm thinking on the scale of seconds. So that's a big problem, yeah. Performance is not awesome for this one.
And if you would find something that makes this faster, would it also make the attack faster?
Yes, assuming things. So in Kuperberg's algorithm, there's a distinction in what Kuperberg's algorithm has to do compared to what honest users can do. So here it's fine to just sample, for example, small exponent vectors. In Kuperberg, you need to generally take pretty much random group elements. and then you need to reduce it to a representation that allows you to compute it efficiently, which is a more difficult problem than having a sampling routine that gives you stuff that you can evaluate quickly, and seems kind of trivial. So not every improvement of doing it honestly will also improve the attacks, I think, but for some, but that's fine, I guess. The slides will be online, we can talk about it later. So the question is, what do I skip now? Does anybody not want to hear about ski sign? I think ski sign is important because it's also in the NIST competition, so I guess I'll just skip to that. Yeah, there's some security things. One thing that I should mention is that there used to be a scheme called SIDH, or Psych. Some people have heard the name, I guess. And it was broken pretty dramatically in summer of 2022. I remember as if it was yesterday. It shattered my entire reality. But, well, obviously I'm still here speaking about isogeny, so not everything is broken. And there's in fact a nice website made by Lorenz among other people that points out what the exact assumptions are behind existing schemes. And well, as you can see, some of them are pretty dead. So red means polynomial time. But there are some others that aren't broken. And that also shows things like the complexity claim that I just pointed out for CSAT. Okay, no time to talk about more hardware stuff. So, ski sign. Ski sign is a signature scheme that has been submitted to the new NIST call. The Q stands for quaternion. The pronunciation is again, to make it sound nicer, than SQI. And the idea is that, well, I'll get to what the scheme does, but the underlying mathematical idea is that there are more special isogenies in this other setting. So now, ski sign really works on this FP squared isogeny. Right? So there's tons of isogenies, and they look very random, and you can't really hope to have like an easy way of walking around there in a meaningful way. But there's other stuff, and I'll talk about that now. So we have these special isogenies defined by rational points of a specified order. And one way to rephrase this is that the kernels of these special isogenies are actually the intersection of a bunch of kernels of other isogenies. And these other isogenies, in this case, actually turn out to be endomorphisms. So they're isogenies from the curve to itself. Multiplication by L does that. Pi was the Frobenius, so it takes a pair xy to its p's powers. And then subtracting an integer again gives you something where you just subtract a point after evaluating the Frobenius. And this is again an endomorphism, defined by rational maps, group homomorphism. And saying that you have a point of order L with rational points in it, okay, a point of order L that's rational, just means it lies in the kernel of multiplication by L, that's what order L means, and it lies in the kernel of Frobenius as well. So those are the points that vanish under pi minus 1, which are the points that are fixed by pi, so they're rational. Now, looking over FP squared, we have a larger field, so there's more ways of writing down endomorphisms of the curves. And in fact, this is, I guess, one defining property of supersingularity curves, that there's more endomorphisms than just these two types of things. And one classical standard example is that if you have this particular curve, you can verify that taking the pair xy to minus x and scaling y accordingly by the square root of minus 1 defines an endomorphism of this curve. And what's also a nice exercise is to prove that this one doesn't actually lie in the set of endomorphisms spanned by integer multiplications and Frobenius. That's a fun exercise if somebody's into that. And what happens to be the case in this setting, once you have these extra endomorphisms, is that you can always define every isogeny as the set of points, or like having kernel that is the group vanishing under a bunch of these endomorphisms. Okay, so previously we had special isogenies, and then there are others that are not special. And once you move to this other setting over FP squared, every isogeny is special. So you can always describe it by equivalently giving a bunch of endomorphisms of your curve, instead of writing down the actual points. And yeah, in this setting, we understand what the structure of this endomorphism ring is. It's a ring, first of all, and it turns out to be like a four-dimensional thing. And so there's math about this. We know what this looks like. And what's also nice is that this description extends to the ideals that define these isogenies. Right? So there's a subset of the endomorphism ring that carves out your isogeny kernel. And when you give me two of those, I can tell you if they give rise to the same isogeny or not. I convert between these different sets of things that kind of carve out your kernel. So this is a little bit like an implicit function type thing. Right? I give you the maps and it defines points that vanish out of these maps. Okay, so we have this correspondence, more or less, of specific subsets of the endomorphism ring. They're ideals, in fact, or like one-sided ideals. It's actually non-commutative. And every isogeny comes from such a thing, and this whole observation extends to what's known as the Deuting correspondence. And this is a nice old paper of Max Deuting from the 40s, I think. And yeah, this correspondence is an equivalence between two very different looking realities. And one of them is just what we've been looking at, so supersync analytic curves defined over fp squared. And this is the new thing that I kind of just introduced a little bit, there is quaternion maximum orders in one particular algebra, so this is a huge mathematical mess. Don't be scared of it. I'm not going to talk much about it. But there are like abstract rings you can write down explicit formulas, and you can compute with them efficiently on a computer. And the point is that these quaternion maximum orders are an abstract representation of sets of endomorphisms on these curves. And indeed, the isogeny turns into an ideal of the abstract thing, and vice versa. And the whole point of why I'm telling you about all this is that we can actually compute one direction of this correspondence. So we can easily go from this quaternion setting to the setting of elliptic curves with isogenies. But the other direction seems hard. It boils down to finding cycles in an isogeny graph, which is supposedly hard because the isogeny graph looks kind of random. Okay, so explicitly, this is kind of what this correspondence looks like. Again, this is not for anybody to understand or remember, just to show that everything is kind of explicit. You have your P, there's a parameter choice from the beginning, and then these maximum orders are defined as a four-dimensional thing. So you can really write them down as a four-tuple of integers or maybe rational numbers. And this particular ring, for example, corresponds to this particular curve. And the same happens for other types of rings, and there's specific things you can do here, and they all look kind of like this. And this is obviously very explicit. You can store these things on a computer. The evidence is that this is a computer and it's on there. So. Right. Okay, so how do we build a signature scheme from this? Yeah, it's like most other signatures. This is based on the FHME heuristic. So you start from an identification scheme, and then you replace the challenger by a hash function, more or less. And here we have the setup is that E0 is a known starting curve, everybody knows this, and then the user of the scheme, the signer, chooses a secret, which is an isogeny, random isogeny. Just walk around on the graph till it's randomized enough, and you get your public key EA, A for Alice, I guess. And then to sign a message, you choose another random isogeny, just commit to the codomain curve you want, you keep the commitment yourself, and then yeah, the challenge comes from somewhere, so I guess later it will be hash function, the interactive protocol is just a challenger, and you're getting all of these things, and then the task is to find a connecting isogeny between your public key EA and this other curve E2. And well, yeah, if you don't have the secret, then EA is kind of random, so you're supposed to find a connecting path between two random things in the isogeny graph, which is hopefully hard. If you do have the secret, you have more leverage, because you know more about how you got to EA, and you know all of these things. So there's a hope that you could somehow connect this. Indeed, knowing all of these things, it's very easy to output a connecting isogeny here. And it's just given by taking your secret, taking the dual isogeny, so that's equivalent information, and it just goes the other direction. And you compose it with these other errors here. And that is a valid answer to the signing challenge in principle. But it's obviously broken because the only way to represent this isogeny is just as a chain, so you're basically outputting your secret as part of the signature. It's like kind of leaky, not exactly what you want. And what SkiSign does instead of that is to start from this, so use this information, and then replace it by a different path. And this is something that you do using this quaternion correspondence, Deuting correspondence. Okay, so the main idea is that you do all of this kind of in the quaternion setting, and then, well, except for the, one of these things is actually sampled as an isogeny, but then you put it back to quaternion land. And you do all the computations, and at the end you just project down the answer to the signing challenge to get an actual isogeny, and the verifier can check using computations on curves that you've constructed the square correctly. To do this rewriting that I pointed out here, constructing a new path between the same pair of curves, we use an algorithm that's known as the KOPT algorithm, Kohl, Lauter, Petit, and Tignol. And well, this is a very general tool in isogeny-based cryptography whenever we deal with these quaternion things. But in our setting here, what it does is, if you have endomorphism rings, so like quaternion information associated to two curves, then you can find an isogeny between them. And this isogeny better be of smooth degree, because that's the only ones you can actually compute, more or less. And what it also does, and that's very useful for re-randomizing the response to the signing challenge, is that you can randomize within a home set. Right? So given, if you already have an isogeny, you can find another one. And doing it properly, you can sort of reasonably randomize that within the set of all isogenies, and then that makes the response that you pass out, you hand out as part of your signature, actually kind of random, and people won't be able to learn your secret from it, for example. Hopefully, that's a little bit of a curiosity.
Oh, so I was about to ask, is that a computational assumption, or is it a statistical property?
This is a statistical thing. So there's this algorithm, and it's done in a way where we hope that it's really kind of uniform among all the isogenies, but it's kind of it's not exactly clear how to guarantee this. Right. So using the second property, pretty much, as I said, we output a new random isogeny between these things, and this is really the core part of ski sign. That's what makes it pretty messy, and everything else is just standard isogeny computations as we've been doing them for a while. Which prompted Bo to say, if you only have this KLPT part implemented nicely, then anybody could implement ski sign. Having implemented ski sign, I'm not sure if that's true. It's still pretty involved. Okay, so doing all of that, what do we get? Here's some numbers from our website, skisign.org. And you can see that the sizes are really attractive. Right? Public keys are extremely small. This is also what sets it apart from almost all the other families of post-quantum signature keys. I mean, I guess you could always fake this by giving out a hash of the public key and then putting the public key in the signature, but that's considered cheating. Yeah, so this is really like, because it has all this math behind it, we don't need to like make everything huge, and there's no weird like repetitions and stuff. So it's really like a one-shot nice identification scheme, and that gives us these very nice sizes. What's less great, and this is a huge problem, I think, is that the performance is really, really bad. So megacycles, this you can think of the word megacycle kind of like second. Oh no, wait, that's gigacycles. Okay. I'm off by a factor of 1,000. Yeah, it's like a millisecond more or less per megacycle on the scale of that. So yeah, keygen and signing are really slow. This is for kind of like a reference implementation though, so there's hope that you can make things faster, but it's never going to be as fast as many of the other constructions. Verification is relatively fast, but still infinitely slower than most of the other things we have. But I guess there could be a niche for this if you really care about sizes and you want to have tons of public keys embedded somewhere. It should just be an application where you don't have to sign very much, because that takes long time. Okay, pointing out more things about the sizes, because that's the good part. Here's this picture from the signature zoo, and yeah, the legend didn't make it onto the picture, but I can explain it. So these blue dots are pre-quantum signature schemes. So this is elliptic curve something, I don't know which one, and this is RSA. And we have public key size on the right side and on the horizontal axis, and signature size on the vertical axis. And then red crosses are things that were submitted to the NIST call but got broken. So there's a couple of those in this area. And then this one little cross here is the smallest ski sign. Yeah. And then you can see that there's basically nothing in this entire square that comes anywhere close to it. And it's smaller than the RSA. Well, depending on the size of the RSA parameters, I guess. So this is pretty attractive, but yeah, performance, as I said. Oh, and these little purple stars are schemes to be standardized by NIST already. So it's definitely much better than anything we have, just so. Yeah, I was going to talk about how to verify, but I guess I'll skip that. There's some nice optimizations to reduce something quadratic to something that's more like n log n. You can look at that later, it's very fun. And then I guess I should be done now, but there's one little part about some more recent developments. If you want to hear that, it's probably going to take another 5 or 10-ish minutes. So people who don't want to hear that, they can leave now. Okay, so let's do it then. I was talking about SIDH, and well, it got broken almost 2 years ago by now. But as part of the fallout of these attacks, well, besides having tons of broken stuff, we also got a lot of new logarithmic tools. So they came out of this attack as, well, it first developed as something useful for the attack, and now it turns out that these things are actually useful for a ton of other things, including constructive cryptography. And the main point of, or the main technique underlying the attack and also these new developments is computing isogenies between products of elliptic curves. Right, so this doesn't seem to make sense because I only defined isogenies for elliptic curves, but this generalizes and you can have like higher dimensional abelian varieties and then compute isogenies between these things. It's something where research has been done on formulas for this, and you can do it in some special cases, but in general this is pretty horrible and not really practical, but for some cases you can do it, and those are the cases we're now using for, well, both for attacking psych and for constructive purposes. So a product of two elliptic curves is something you can clearly write down abstractly, just by taking tuples of points and stuff, but it actually also has a description as an abelian surface, so it's just like, again, given by polynomials, just like a curve is given by a polynomial equation. But it's higher dimensional, dimension 2, and it could live in a pretty horribly big projective space. But conceptually, it's not too complicated, it's just computationally very annoying. So it's a little bit like taking a product of two lines, and now we have a line that's an elliptic curve, and that gives us something that's kind of like a surface, but with more things to it. And it's an abelian surface, meaning that we still have a group law where we can add and subtract points, and it all makes sense in this way. Another thing that we can do on these abelian surfaces, and more generally you can also think of higher dimensional versions of this, is that you can again define isogenies from finite subgroups with particular properties. So depending on how exactly things are done, we need more or less of these properties. So some of the things we do generalize here, and this can be quite nice. And indeed, one of the main things that came out of the SIDH attack is this core embedding lemma, as it's called now. And well, there's a large quote from one of these papers, but the key point is that the embedding lemma allows you to represent an isogeny of degree A1 and A2 as a higher dimensional isogeny where the degree is the sum of the two. And that's kind of surprising because degrees are normally multiplicative when you do anything non-trivial with them. But allowing, like taking things to higher dimensions allows you to take the degree additively. That makes it nice to compute in some cases. There will be an example of this on the next slide as well. Yeah, so Panny also says this lemma is very simple, and to him that means. It really was discovered as part of the psych attack that this is useful, and then since then it's been used and generalized, and now it's actually made into some constructive proposals as well. And people are working on making the formulas and algorithms for this better, faster, stronger, more side-channel resistant, more cryptographic. Okay, so this embedding lemma, and I don't have time to explain a lot of details about this, and I also don't understand a lot of the details myself, but what it basically does for us is when you have a diagram of isogenies where these things have the same degree and these things have the same degree, and the degrees are co-prime, then we can actually glue together pairs of elliptic curves that appear in this diagram and define an isogeny from one of these products to the other one of these products. And this is something we can explicitly compute because the kernel has an explicit description. So if you can evaluate these isogenies that appear in the diagram, if they're one-dimensional elliptic curve isogenies, then you can actually explicitly write down the kernel of this isogeny of products. And it has an explicit description as a matrix of isogenies of elliptic curves, like this, where you can plug in points on this product. Right? So plug in pairs of points, and you get another pair of points that lies on, this should be a cross again, that lies on the product of these elliptic curves. So what this basically does, and that's the key point, is if you only manage to evaluate these isogenies phi and psi prime on points of order n, where n is the sum of the two degrees, then you can actually evaluate them on any point. So now you have an explicit description of this other isogeny. You can compute this, and you just plug in the points p, comma q in here, and you get something in the output that relates to the version isogeny you have. So the only thing you have to do is find out how to evaluate your isogenies on some large enough subgroup of the curve, n-torsion subgroup. And in fact, as it turns out, this kind of information is exactly what Psych just handed out as part of the public. So you didn't have to compute anything, it was just given, and then people could use this, this special isogeny that comes from this kernel, and you can compute the kernel because the data is given as part of the public data in Psych. And then they can use it to evaluate the secret isogenies, and that breaks the scheme completely. So this is the big idea. In fact, this kind of thing now shows up in tons of other algorithms, also for constructive use cases. And there's a version of SkiSign that's called SkiSign HT, and uses this, and there's something called Scallop HD. And it used to be a joke for a little while to put HD everywhere, and it stands for higher dimensions. And yeah, it all uses this kind of idea. And the only tricky part is that a lot of these things aren't computable, so you can write down a lot of things that look like this, but nobody has any clue how to algorithmically do it. And, so the difficult part is finding the cases where you can do this efficiently with current methods. Okay. Yeah, maybe I'll also skip this as a bit more technical detail about how these things can be represented. This is kind of part of the Psych attack, but basically, you get extra data as part of the Psych public key, and then that allows you to compute this kernel here, and that breaks everything. But yeah, I'm standing between you and your lunch. So I guess this is the end of all the technical stuff I wanted to say. There's one more little ad for a series of seminars on the internet, so you don't have to go anywhere to go there. The time zone is like afternoon in Central Europe. And yeah, it's the Isogeny Club. I'm wearing the t-shirt. I know that at least one other person does as well. Yeah, it's quite nice for young people such as yourselves who want to know more about isogenies, and it's usually also very informal and there's discussions and it's quite fun. Okay, and that's it. Yeah, if anybody has more questions, happy to take them.